Okay, so when we last left off, we were discussing chapter 17 and naming alcohols. In this session, we're going to discuss how to name phenols. And phenols still follow classic aromatic nomenclature discussed in chapters 15 and 16. So when naming phenols, you use phenol as your parent hydrocarbon name, and you name the substituents on the aromatic ring by their position relative to the carbon bonded to your hydroxyl group. So in phenol, just like in any other aromatic nomenclature method, the carbon attached to the alcohol of your phenol, or in general, the carbon attached to whatever functional group you choose as your base aromatic ring, will be assigned locant number 1. So as a result, this methyl substituent we see is meta to our phenol alcohol. So we call this meta-methylphenol. Likewise, if we have an example here of dinitrophenol, the alcohol of your phenol, the carbon attached to the alcohol, gets locant number 1. And as a result, numbering our substituents to give the lowest possible locant numbers gives us 2 nitro groups at position 2 and 4. So this would be 2,4-dinitrophenol. Does that idea make sense to everyone? Does that idea make sense?
What is meta again when it comes to like
Meta
positioning?
implies a 1-3 relationship.
1, 3.
Meta
Okay,
implies
thank
that
you.
we have a 1-3 relationship between our substituents.
Okay.
And the ortho-meta-para nomenclature is only really applicable when you have an aromatic ring with exactly 2 substituents. When you have more substituents, ortho-meta-para becomes ambiguous. Does that make sense?
Yes, thank you.
Perfect. So there are many common names for alcohols. So for example, this compound here is called benzyl alcohol rather than phenylmethanol. Allyl alcohol is used instead of 2-propene, 1-all. So there are many common names, and you can use the common name if it is explicitly noted in the book or notes. Okay, so just as a test to refresh our memory of aromatic nomenclature that we've covered and did multiple examples on in chapter 15, let's try to name the following compounds. So how would we name this compound? So we have a phenol, so this is carbon 1. So what would a reasonable name for this compound be, accounting for our substituents and their position? So we have some proposals of 2,5-diethylphenol. So let's look at our locant numbers, 1, 2, 3, 4, 5, 6. So it's 2,5-diethylphenol, and it was corrected to 2,6-diethylphenol. These 2 carbon substituents are ethyl groups. We number our substituents. They're positions 2 and 6. So this would be 2,6-diethyl, di because we have 2 ethyl groups, and then phenol because our base aromatic ring is a phenol. Does this example make sense to everyone? Any questions on this example? Okay, so let's keep going now. And let's talk about properties of alcohols and phenols. So the central oxygen of your alcohol is similar to that of water. It's an sp3 hybridized oxygen atom. And just like water, alcohols are more than capable of hydrogen bonding. So any generic alcohol, we have a hydrogen donor and a hydrogen acceptor. Now, this hydrogen bonding is pretty important because it leads to alcohols and phenols having much higher boiling points than similar alkanes and alkyl halides. And we can leverage this to separate out alkanes and alkyl halides from alcohols. So this is the first property of alcohols that can be leveraged as part of their separation. They're capable of hydrogen bonding, so they exhibit higher melting and boiling points than other compounds. Any questions on this idea? Okay, so let's keep going then. And let's talk about properties of alcohols and phenols in terms of their acid-base properties. So alcohols are amphiprotic motifs in that they can serve as weakly basic or weakly acidic functional groups. So for example, alcohols and phenols can function as weak Bronsted acids, and they can transfer a proton to water to a very small extent. So alcohols can undergo a little bit of auto-ionization and self-ionization. Now, if we think about an alcohol's pKa to get a sense of the relative acidity of an alcohol, alcohols are a little bit less acidic than water, typically with a pKa value of around 16 to 17. Now, alcohols can also serve as weak Bronsted bases, and they can be protonated by strong acids to yield oxonium ions. This is a very common first step in many elimination or SN1 substitution mechanisms. One thing to note is that the alcohol conjugate acid is quite acidic with a pKa of around -2. So typically this protonation step outside of very strong acids is usually an equilibrium and a reversible equilibrium at that. Does this idea of the acid-base properties of alcohols make sense? Okay, so let's keep going then, and let's just refresh ourselves on the idea of acidity measurements. So the acidity constant, or Ka, measures the extent to which a Bronsted acid transfers a proton to water. So in general, the smaller your pKa value, the stronger the acid that you're dealing with, and the more H3O plus we have generated at equilibrium. So as we see, there are some important trends to note as we go through this chart. First, when we have a tertiary alcohol, such as tert butanol, compared to a primary alcohol, which of these alcohols is more acidic, primary or tertiary? Primary. Yep, exactly right. So primary alcohols are generally more acidic, and we'll talk about why. The next major thing I'd like you to note is that if we compare equivalent primary alcohols, but we're looking this time at an alcohol containing an electron withdrawing group, such as a CF3 group, what happens when we have an electron withdrawing group? What do we notice? Do we get a more or less acidic alcohol? So we have one student commenting it's more acidic, and the reason for that is it stabilizes the carbanion. Yes, that explanation is perfectly correct. The other thing that I'd like you to note is if we compare a normal straight chain alcohol versus phenol, phenol is substantially more acidic, right? And looking at that, what is the distinguishing factor? What's different between this alcohol that's the typical primary alcohol and phenol? Would anyone care to provide a reason? Why is phenol more acidic?
Is it because of more resonance?
Yeah, so you're bringing up this idea of resonance stabilization.
Yeah.
Yes, it's
Yes, yes.
tied to this idea that the conjugate base for phenol is stabilized by resonance. Yeah, so that initial idea is definitely on the right track. and that explanation is consistent with our observations. So generally, phenols are more acidic than your typical alcohol because you can stabilize your conjugate base via resonance. So this table really contains a lot of the main points that we're going to unpack and review when we talk about acid-base chemistry in the context of alcohols. So any questions on just our initial observations? We'll be unpacking these points further, but does everyone see how this table contains a lot of information and can help showcase a lot of the trends in terms of acid-base, in terms of alcohol acidity? Okay, so let's start unpacking each of these trends, and let's look first at the relative acidities of alcohols. Now, one important thing to note is that the solvent can stabilize the anionic conjugate base through ion-dipole interactions and or dipole-dipole interactions. So, for example, suppose you have a generic base. The solvent, that I'll write as H-solve, can stabilize the conjugate base both through hydrogen bonding and through ion dipole interactions. Now, this may seem like an obvious point, but let's bring this up and make this explicit. In order for the solvent to stabilize your conjugate base, the solvent must be able to surround and approach the conjugate base, right? In order for this interaction to occur, which is a relatively short range interaction, the solvent must be able to get close to our conjugate base. Does everyone get that idea? Does that point make sense? So, building on that idea now, alcohols and XH bonds on more substituted carbons are less acidic, as their conjugate base experiences less stabilizing interactions with the solvent. Now, if we think about this tertiary alcohol, it is a hindered alcohol. So as a result, when we have our solvent, when we're trying to surround our conjugate base with solvent, is it easy or hard for our solvent to approach? Is it easy or hard for our solvent to approach when we have a hindered alcohol? It's very difficult, right? There's less space for our solvent to approach and access our conjugate base. The alcohol is more sterically congested, and as a result, the alcohol experiences weaker and diminished interactions with the solvent. So the conjugate base is less stabilized by our solvent, and as a result, the parent alcohol is less acidic. So as we go from water to a primary, secondary, and tertiary alcohol, we notice that our acidity decreases. Does that idea of substitution and alcohol acidity, does that make sense? Okay, so to further encapsulate the point, the more substituted the carbon the alcohol or XH bond is attached to, the more difficult it is for the solvent to interact with and stabilize the conjugate base. So this tertiary alcohol is very hindered, very hard for solvent to effectively interact with and stabilize your conjugate base anion. While for methoxide, which is a primary, or more specifically, it's a methyl alcohol, it's very easy to access, very easy to stabilize, and as a result, methanol is more acidic than tert-butanol. Okay, there are a few other factors affecting conjugate base and anion stability, which in turn affects acid strength. The first of which is induction. So induction is built on this idea that electronegative atoms draw electron density in the molecule towards that atom. And this withdrawing effect draws electron density from atoms bonded to the electronegative atom and adjacent atoms. So there's a through bond inductive effect. So electron withdrawing substituents draw electron density in the molecule towards the electronegative atom. So that leads to electron rich and electron deficient regions. Now, the presence of electron withdrawing atoms in one region of the molecule draws electron density from adjacent regions of the molecule. In turn, inductive electron withdrawing effects and inductive electron withdrawing groups functionally draw electron density away from the atoms attached to the acidic hydrogen. And in turn, the anion generated by breaking, in this case, our oxygen-hydrogen bond, is substantially more stable, as it is on a functionally more electron deficient and electronegative atom. So this inductive effect stabilizes our conjugate base anion by delocalizing some of that electron density and drawing some of that electron density away from your electron-rich conjugate base oxygen atom. Does this idea of inductive effects make sense? Does everyone see how electron withdrawing groups can help stabilize an anion by stabilizing that electron density and delocalizing that electron density? Does that idea make sense? Okay, so inductive effects depend on, oh, the structure drawing tool got a little too excited there when I told it to replace an atom with chlorine. So let me just correct that structure. So one thing I'd like you to note is inductive effects depend on the electronegativity of the bonded atoms and the number of electronegative atoms. So as we see, when we increase the number of bonded electronegative atoms, we see a corresponding increase in acidity or a corresponding decrease in pKa. Does everyone see how when we add chlorine atoms, our proton acidity, our proton becomes more acidic, and in turn, our pKa drops dramatically? Does that idea make sense? Now, another thing to note about inductive effects is that they are distance dependent. So inductive effects depend heavily on the number of bonds separating your electronegative atom and the acidic XH bond. So as our withdrawing group gets farther and farther away from our acidic proton, in turn, the inductive effect on our proton's acidity decreases. So the farther your electron withdrawing group is from your acidic proton, the less acidic that proton will be. Does that idea make sense to everyone? Okay, so let's try to put this into practice. So we have two alcohols in the same molecule, and I'd like you to tell me whether alcohol A or B will be more acidic based on what we've learned about inductive effects.
Would it be A?
Yep, exactly right. And would you like to provide a reason for why? Why is proton A more acidic?
Because it's closer to the withdrawing group.
Yep, exactly right. So in general, inductive effects scale with distance, and proton A is closest to our two electron withdrawing groups. So you're absolutely correct in that proton A would be more acidic. Any questions on this example? Any questions I can address on this example? Okay, so let's keep going then, and let's talk about, and let's just reiterate this idea of alcohol acidity and inductive effects. So electron withdrawing groups make an alcohol a stronger acid by stabilizing the conjugate base. So when you have more electron withdrawing groups, in general, you see a more acidic alcohol and a lower alcohol pKa. Now, let's talk about methods of generating alkoxides from alcohols. What are common methods to deprotonate alcohols? Well, really, any strong base will do the trick, but it has to be a reasonably strong base. Alcohols are weak acids, so as a result, they don't generally react efficiently with weak bases. So we need a strong base such as sodium hydride, sodium amide, or Grignard reagents to generate an alkoxide from an alcohol. So as you see, you can use potassium or sodium metal, you can use sodium hydride, sodium amide also works, methyl magnesium bromide also works. So essentially, as long as you have a sufficiently basic reagent, so with a conjugate pKa of greater than about 25, then that basic reagent is more than capable of pulling off your alcohol proton and generating an alkoxide. Does this idea of generating alkoxide anions make sense? So we'll talk about later on in this chapter methods of taking these alkoxides and using them in reactions to make derivatives such as ethers and esters. Does this initial idea make sense? Okay. I'd like you to save this last example in your memory, and I just want you to remember alcohols and Grignards react. Just save that in the back of your mind for a little bit. Alkoxides themselves are also used as bases and as reagents in inorganic chemistry. So for example, if you want to facilitate an elimination reaction, you can commonly use something like T-butoxide. Super common hindered basic reagent, pulls off a proton, great for elimination reactions. Likewise, if you have like a primary alcohol, you can use an alkoxide such as ethoxide, for example, as a perfectly suitable nucleophile for SN2 reactions. So alkoxides are useful as bases and as nucleophiles. Does that idea make sense to everyone? And does everyone see the utility behind these methods to generate alkoxides? Okay, so phenols are a bit of a different beast when it comes to acidity. Phenols have a pKa of about 10, so they're a million times more acidic than alcohols. This is due to resonance stabilization of your phenoxide ion. Essentially, we're stabilizing our conjugate base anion. Phenols can react with weak basic solutions, such as a sodium hydroxide solution, forming salts that are soluble in dilute aqueous solution. Thus, and this is important as we'll actually use this theory, actually, we may have already used this theory in the extraction lab, but a phenolic component can be separated from an organic solution by extraction into a basic aqueous solution, followed by isolation. So phenols, due to their unique acidity, are separable from common alcohols. And you may see this in the extraction lab. If you've taken the course with me last semester, we looked at an example where we showcased the separation of a phenol from a typical amine and straight chain alcohol. So we can exploit differences in acidity to design separations. Does this idea make sense to everyone? So the phenoxide ion is resonance stabilized, phenols are more acidic, and as a result, they're uniquely separable. Okay, so let's keep going then, and let's talk about substituent effects. Since phenol acidity is heavily dependent on substituent effects, and substituents can result in increased or decreased acidity for that matter. Phenols with electron withdrawing groups are more acidic, and this is due to delocalization of the negative charge via resonance. So electron withdrawing substituents can effectively stabilize the phenoxide anion via resonance if the electron withdrawing substituents are at the ortho and para positions relative to the phenol alcohol. I'd like you to recall that a similar trend of activation and the similar trend is observed in nucleophilic aromatic substitution, where electron withdrawing groups at the ortho and para position activate our alkyl halide. It's the exact same principle. Or electron withdrawing groups at the ortho and para position relative to our alcohol can stabilize our conjugate base anion via resonance delocalization. And as we notice, when our substituent is at the ortho and para position, our electron density initially present on our phenoxide alcohol can be delocalized into our electron withdrawing group. Does everyone see how electron withdrawing groups at the ortho and para position are uniquely activating and substantially increase our proton acidity? Does everyone see why it's position dependent? Perfect. Now, one thing to note, substituents at the meta position exert a smaller but still appreciable effect on pKa. So when we look at this following table, let's try to follow what's going on here. We have chlorine, which is a sigma withdrawing group. It just withdraws via inductive effects, and it's a pi donor. So it's a sigma acceptor. And we see a pretty small drop in our pKa value. So we have a small increase in acidity. When we switch to this ether is a pi donor. And by donating electron density into our ring, and by sort of, as a result of this, donating electron density into our phenol alcohol, we destabilize our conjugate base anion, and as a result, we have a less acidic phenol. Donating groups decrease our proton acidity. Does everyone see that? How when we switch to a pi donor, our acidity drops slightly? Next, we have, in this case, a nitro group, and it's able to function as a pi acceptor, and it's a strong pi acceptor. So we see a 1,000-fold increase in acidity. Note, if we compare the para versus meta nitro compound, when the nitro group is in the meta position, the nitro group is functionally acting as a sigma acceptor. It's not really able to delocalize our conjugate base anion via resonance. It's just serving as a withdrawing group. And as we see, the meta nitro compound is 10 times less acidic. Does this survey, does this overview of substituent effects and their influence on phenol acidity make sense to everyone? Any questions on this example? Okay, so we're now going to review, and I do say review in that many of these reactions we've seen before in Organic Chemistry 1. We're going to review methods to prepare and derivatize alcohols into different functional groups. So we're going to talk about common methods to prepare alcohols and talk about different tools that we have at our disposal to make alcohols with defined regiochemistry and stereochemistry. And alcohols really are quite useful functional groups because they can be prepared for a range of functional groups and they can be derivatized into a range of functional groups. So an alcohol is a useful functional handle as they can engage in a range of reactions, each with their own chemoselectivity, regioselectivity, and stereospecificity. Okay, so we're going to talk about methods to prepare alcohols. And the first method we're going to talk about, and the first block of methods that we're going to talk about, are methods to prepare alcohols from alkenes. Now, if you need a review on any of these concepts, this is primarily found in the 112 chapter 7 notes that I have on Canvas. So, oxymercuration, besides using mercury, it's a pretty good method to install an alcohol. So oxymercuration is a two-step process where you have oxymercuration followed by reduction of the alkyl mercury species with sodium borohydride. Now, the addition of water occurs from the most hindered face and anti to the mercurinium ion. Addition of water follows Markovnikov selectivity, with water adding to the most substituted carbon. I always like to think of mercury as an atom that really, really hates steric hindrance. Mercury wants to be on the least hindered, least substituted carbon. So our oxygen atom, our water, will add to the most substituted carbon from the most hindered phase. So oxymercuration follows a two-step mechanism. So let's draw out the first step. So we have our mercury acetate. And this is something that I'd like everyone to note. We're going through a cyclic mercurinium ion. So we need to draw two arrows. The first of which, we have attack of our electron-rich alkene onto our electron deficient or electrophilic mercury acetate, the mercury atom in mercury acetate. In our second step, the mercury cyclizes back onto our second alkene carbon, and we generate this cyclic mercurinium intermediate. Now, this mercurinium intermediate can be formed on the top or bottom face. I'm going to draw the mercurinium ion formed from the top face, just arbitrarily, just to showcase this next point. So water then opens up our mercurinium ion from the opposite face, and water attacks the most substituted carbon. So in this case, we have a choice between a tertiary and a secondary position. The tertiary position is more substituted. It has more cationic character. As a result, it has a weaker carbon-mercury bond, so it's easier for water to attack on that carbon and break your carbon-mercury bond. That gives us our alcohol installed with Markovnikov selectivity. And one thing I'd like you to appreciate is that our alcohol and our mercury are installed with anti-stereochemistry. Now, you may wonder, why isn't the book showing this anti-stereochemistry? This brings us to our next point, where even though you install the mercury anti to your alcohol, in the second step, the reduction with sodium borohydride, the second reduction step leads to a racemate when at this position. The reduction step scrambles your stereochemistry at that position. So you can install your alcohol with stereospecificity, and however, the carbon-hydrogen bond is not formed with any stereospecificity. Does this example of oxymercuration and does this mechanism of oxymercuration look familiar? And just remember, this is a wonderful method to install alcohols with anti-Markovnikov Regio selectivity. Oh, sorry. This is a wonderful method to install alcohols with Markovnikov Regio selectivity. So our alcohol, or water in this case, is installed at the most substituted carbon. The reason why I got a little ahead of myself here is that when we compare oxymercuration, when we start to think about why oxymercuration is utilized, let's talk about some unique benefits in contrast to another reaction with Markovnikov selectivity, such as acid catalyzed methods. We'll talk about why we get a racemate in a moment, actually. So to talk about a benefit of oxymercuration compared to traditional acidic conditions. So let's do a side by side and let's compare if we used acidic conditions. So acidic conditions go through a carbocation intermediate, right? You protonate your alcohol, you get a carbocation, and in many cases, you will just see a tack onto your carbocation, and we have Markovnikov selectivity. We attack the most substituted carbon, or the carbon that can most readily stabilize a carbocation. However, unfortunately for us, carbocations have a major drawback, and acidic conditions have a major drawback. Looking at this structure, what is something that carbocations can do? What is a mechanism that we can draw that would result in another product? What's something unique about carbocations? What's something that's pretty unique? Rearrangement and hydride shifts, right? So we can undergo a hydride shift, generate a more stable tertiary carbocation. Water then attacks, and we unfortunately end up with the wrong product. This is not what we want at all. So one benefit of oxymercuration, one really important benefit of oxymercuration compared to acid catalyzed hydration is that oxymercuration installs your corresponding alcohol without any risk of rearrangement. Further, it installs your alcohol with some stereo control. So we don't have to worry about any rearrangement issues when we go through oxymercuration. So oxymercuration gives us Markovnikov Regio control, addition of our alcohol to the most substituted carbon without the threat of rearrangement. Does that point make sense? Does that unique benefit make sense? Okay, so to answer the question of why do we get a racemate during the reduction step? So generally when you reduce this alkyl mercury, we see a loss of stereochemistry at the carbon containing your mercury atom. That is because you're typically going through a radical intermediate, and this radical intermediate can be approached from either face and can be engaged with on either face. And as a result, we would get a mixture of incorporation of our hydrogen atom at either of our two faces. Because we see a mixture when we install our hydrogen atom, by definition, we'd have a racemate at this center when we reduce our carbon-mercury bond. So we see experimentally that we often see loss of stereochemistry at the carbon containing our mercury atom during reduction. And part of the reason for that is we're going through this radical intermediate that can be engaged with on either face of the radical. Does that make sense? Does that answer your question? So oxymercuration, Markovnikov Regio control, and generally for the stereo control, you get a mixture of the syn plus anti final product. But it's important that you draw your mercury and alcohol anti to each other, because before the reduction step, it does give you anti-stereochemistry. Does that point make sense? Perfect. So let's keep going then. Now, oxymercuration occurs via anti-addition following Markovnikov regiochemistry. So just to show this once again. So we generate our mercurinium ion intermediate. We don't have to worry about any rearrangement. Then water very quickly attacks at the most hindered carbon. I'm going to draw the mercurinium ion on the bottom face in this case, just to reflect what we have as our final product. And note that the mercurinium ion can form on either face, so we get a mixture of enantiomers. But in all cases, we see Markovnikov selectivity and anti-stereochemistry. In this case, this center is not a genuine stereo center, but if you have another alkyl group, then you can potentially see a mixture of stereoisomers at this position. So, to practice what we've learned, I'd like us to draw a mechanism for step 1 of the following reaction. So just the step where we treat this alkene with mercury acetate and water, and I'd like us to predict the products for this reaction. So let's take about 3 to 4 minutes and let's try to use the annotate tool to draw out the mechanism for this reaction and predict the products from the first step from this reaction. So I'd like to see some students sharing their responses using the annotate tool, or you can also share a photo of your work in the chat, just to make sure students are comfortable drawing this oxymercuration mechanism and predicting the products with the proper regiochemistry and stereochemistry.
Professor, are we adding the mercury to the most substituted carbon?
So we first make the mercurinium ion, and
Yeah.
then water opens the mercurinium ion from the opposite face at the most substituted carbon, or the carbon that can most stabilize a cationic charge.
Okay.
Would anyone like to try drawing out a mechanism using the annotate tool? Under meeting options, you can find an option to draw an annotation. And I'd like to see some students try to annotate this mechanism. So that way we can discuss it and I can get a sense of how the class is proceeding in drawing these mechanisms. You can also share a photo of your work in the chat. If we need more time, let's keep working on this example, but I'd like to see a few student responses before we continue. Would anyone like to volunteer and try to provide? So we have the mercury acetate drawn. So the student's beginning to draw the first step. It may be easier to draw the acetate separately because you lose an acetate in the first step. But we have our cyclization to make, oh, you can you can just hit the erase and just erase parts of it rather than erase the whole thing. But in the first step, we have cyclization to generate our mercurinium ion. And that cyclization occurs with loss of, I'm just re-annotating what the student is drawing. So for our first step, the student correctly drew, we have cyclization and attack of our alkene onto mercury acetate. We generate the mercurinium ion. And the student carefully drew the mercurinium ion as on the bottom face, though it can just as easily approach from the top. And then for the next step, the student carefully drew the attack of water from the top face on the most substituted carbon. So we're dealing with Markovnikov selectivity once again. And they have drawn, just converting what they've drawn out. Oh, they're even doing the next step. Okay, good. So they drew out our water addition product, and then they showed the deprotonation step. I know it's a little hard to annotate a lot of these structures, but the thought behind it looks perfectly correct. Yep, and the final product looks good as well. Oh, the second reduction step, you don't have to worry about the mechanism for, as it's a little tricky. We'll talk about that maybe later on in later chapters. But yeah, this first alkyl mercury product is exactly correct. So let me just clear the annotations and let's redraw what the student has conveyed. And that mechanism was fully correct. So just to redraw what the student conveyed, You have attack of your alkene on the electrophilic mercury atom. You get cyclization to make a mercurinium ion. The student chose to draw the mercurinium ion on the bottom face. That's more than okay. It can just as easily form on the top face. Water then attacks and opens up our mercurinium ion from the opposite face. Well, I appreciate that the stereochemistry even then was very clearly drawn, and the regiochemistry was clearly drawn. So the student drew water attacking from the top face, and we get the following Markovnikov regio selectivity. And then as the final step, and I really appreciate this finishing touch to make sure we actually get to neutral isolable intermediates, we have deprotonation. And that gives us the final product from the first step that looks something like this. Now, of course, you typically don't isolate the alkyl mercury, and of course you end up with a mixture of this product and the enantiomer. That's all fine. And then the second step, when you treat with sodium boryl hydride, you install your carbon hydrogen bond. Yep, so this product plus the enantiomer are the two products that we get out from this reaction. Does this example make sense to everyone? Does this mechanism make sense?
Professor, so when we do the cyclization, one of the
One of the acetates, yep, is lost.
Yeah, so they're gone, right? That's what that arrow over there is pointing
Yeah,
out?
exactly. Because mercury can accommodate, mercury starts with two ligands, and in this step, rather than coordinating the acetate, the mercury is coordinating our alkene. So that's why an acetate leaves.
And then for the process, the part where it the water attaches to the most substituted portion,
Yep.
that would be the HGOAC. Is that because it's, like you said, mostly substituted? If that makes
The mercury acetate, so the mercurinium ion has one acetate as the ligand, and then when water attacks the most substituted carbon, this carbon mercury bond in our mercurinium ion breaks, and we end up with the mercury with a bond to the acetate and a bond to the other carbon. So this is our isolated alkyl mercury species, and we've installed our nucleophile, in this case water, at the most substituted carbon.
So we can technically finish once the water where it's substituted, right?
Yes, but ideally you want to get to an isolable neutral intermediate, and that's why the last deprotonation step is very important.
Got it. Awesome. Thank you.
Yeah. In terms of what you practically isolate, you typically add the boryl hydride at the end of the reaction and let that sit, so that way you get a normal organic compound rather than an alkyl mercury, because alkyl mercuries can be pretty toxic. But I'm just trying to showcase that you do get an alkyl mercury from the first step, and that alkyl mercury is the carbon mercury bond is installed with stereo control, and in the reduction step you racemize that center. Does that make sense?
Yes.
Perfect.
So do we not need to show the mechanism when we add the NaBH4?
Yeah, usually on the exams I'll explicitly say you can skip mechanisms involving organometallic intermediates. So you can skip or draw. In this case, I instructed you to draw the mechanism for step 1. Does that make sense?
Yes, thank you.
Perfect. So let's talk about a sort of corollary to oxymercuration, which is hydroboration. So hydroboration is unique in that it installs an alcohol with anti-Markovnikov regiochemistry and syn stereochemistry. So it's almost the exact opposite of oxymercuration. So borane is a very reactive Lewis acid, and the alkene is a Lewis base. It's electron rich. Boron will add to the least hindered face, and the boron will be installed on the least hindered carbon. And that's because boron wants to minimize destabilizing steric repulsions. You want to install your boron on the least hindered face and on the least substituted carbon atom. And that's just to minimize steric crowding and steric congestion and hindrance. Now, what's really interesting is because the boron and hydride add to the same least hindered face of the alkene, when you go to oxidize this alkyl boron, this oxidation step occurs with retention of stereochemistry. So because your boron is installed on the least hindered face and the least substituted carbon, your alcohol in turn is installed on the least hindered face and the least substituted carbon. So this is a wonderful method to install alcohols with anti-Markovnikov regio control and syn stereo control. Because remember, this oxidation occurs with retention of the boron stereochemistry. Does this idea make sense to everyone? Any questions?
Can you point out where is the most, the least hindered face of the alkene?
So in this case, both faces are equally sterically congested. We'll see an example actually, if not in the next slide, the slide after, to address that point. The least hindered face is we'll see in an example where essentially we have molecules with more three-dimensional shape where the two faces are non-equivalent. The boron will try to add to the least hindered face. So an example of this would be, we're going to see this example momentarily, but so if you have a ring system like so, where the top face has this hindered blocking group, then hydroboration will selectively occur from the bottom face because the bottom face is the least hindered. This is an example of facial selectivity brought about by differences in the steric environment of each face. Does that make sense?
Yes.
So it's essentially built on this idea: if molecules have differences in steric hindrance, hydroboration will occur from the least hindered face and it will install the boron on the least substituted carbon.
Okay.
Does that answer your question?
Yes, thank you.
Perfect. Now, one interesting sort of consequence and one thing that we just want to reiterate is the hydrogen and alcohol are installed with syn stereochemistry to the same face of the alkene. So as a result, if you take, for example, 1-methylcyclopentene and subject it to hydroboration, we see that our hydrogen and boron atom are installed with syn stereochemistry. So as a consequence, when we oxidize our resulting product, we generate the following trans 2-methylcyclopentanol as a single product. So the main distinction between oxymercuration and hydroboration, in addition to their differences in regio control, is that the oxidation of this alkyl boron occurs with retention of stereochemistry. So when I keep bringing up this idea that this approach occurs from the least hindered face, if we have a ring system where the top face or one of the faces is blocked and is especially sterically hindered, your hydroboration will occur in a way where your boron approaches from the least hindered face. So in this case, the top face is blocked, so the boron approaches from the bottom face. And this occurs if the two different approaches of our boron or BH3 equivalent are non-equivalent. Any questions on hydroboration oxidation? Okay, so let's keep going now. And let's practice drawing a mechanism for the following reaction. And I'm just going to make one modification to this structure. And I'm going to replace this methyl with a hydrogen. So given the following reagent conditions, I'd like you to draw a mechanism for at least the first step of this reaction and predict the products from this reaction. And if you need more time on this example, don't worry. I'd like to have us work on this example until I see a few student responses. And you can submit your responses using the class whiteboard annotate tool or as a screenshot in the chat. And I'd be happy to provide feedback. And you can also ask a question as you work through this example. In addition to drawing out the product structure, you can post a picture of your proposed product structure and mechanism in the chat, or you can write the name of the product in the chat. That would also work.
Professor,
Yes?
I'm confused on like how can you how do you pick the least hindered carbon? Like how can you tell?
The least hindered carbon is the least substituted carbon. So like, for example, in this case, we're dealing with secondary versus tertiary, right? Or pseudo-secondary versus pseudo-tertiary, right?
Yes.
So then which of these carbons is least hindered? Which of these carbons is least substituted?
The secondary
Yep, exactly right. So where would our boron be installed?
in the top carbon, secondary
Yep,
carbon.
the secondary carbon. Yep.
Okay, thank you.
Perfect. And there's plenty of space in the class whiteboard. So if multiple students would like to try to draw their mechanism, I've set it up so there are at least 2 full lines for students to draw their mechanisms. So really don't be shy. I find the act of drawing a mechanism is incredibly instructive in understanding the reaction. For that product, would I be able to see some stereocenters for that product? for the boron and the hydrogen that's installed. You're on the right track in terms of regio selectivity, but if I could get some stereo centers, that would be perfect. And a student just submitted their response in the chat. Yeah, the mechanism I see in the chat looks fine, but I'd like to see the alkyl boron intermediate drawn. And now our question becomes, how should we draw out the stereochemistry? So we're forming a bond to a hydrogen atom and a bond to the boron atom. And what is the stereochemistry for that bond forming event? Syn or anti? Syn, right, exactly right. So in this case, we'd show installation of our boron and our hydrogen, yep, on the same face. So in this case, the student, so just to make sure, as drawn, rather than drawing the methyl first, let's just pin down the boron and the hydrogen. So if the boron and hydrogen are installed syn, where would the boron and hydrogen end up? Would they be on the same or opposite face? Since it's syn, they'd be on the same face, right? So let's draw that and then put the methyl on the other face, right? So draw the hydrogen and then draw the methyl. So we have another student drawing it out, but I'd like the student who annotated it in purple to do that correction, just so that way we can get that idea sort of encapsulated. Okay, so the boron and hydrogen are installed on the same face, and so the methyl ends up on the opposite face. Does that idea make sense? Does that concept make sense? So these student responses look good so far, and we now have the correct regio selectivity, which all of the responses got perfectly. And we're noting the stereoselectivity. It's a syn addition from boron and hydrogen are installed on the same face. And then after the oxidation step, you get your alcohol. Perfect. So these student responses look great. Let me just redraw them using the instructor annotation. So in this case, so for our first step, boron will add to the least substituted carbon, and the boron and hydrogen are installed on the same face. So we're going to arbitrarily say that our boron and hydrogen are going to be installed on the bottom face. You will just as easily see the enantiomer. And the response I see in the chat submitted as an image looks great as well. So we've installed our boron and our hydrogen, syn, on the same face and on the bottom face. As a consequence of this, the methyl group ends up on the top face. Finally, for our second step, when we treat with hydrogen peroxide and sodium hydroxide, we end up installing our alcohol. I provided the mechanism for this second step in the chapter 7 notes on Canvas and in the chapter 7 lecture recording for reaction of alkenes. Does this example make sense to everyone? Does the regio selectivity and stereo selectivity make sense?
repeat why this one was syn again? Like how we knew the syn?
For hydroboration, the boron and hydrogen are always installed on the same face.
So could we have done with the boron coming out
On the top face? Yeah.
and the top and
Yep,
then the
exactly.
other
So
okay.
this is an important point, and I'm really glad you brought this up, because in addition to the product that we have drawn, we also have the enantiomer, which would look like this. And this enantiomer comes from the approach on the top face. Now, one thing to note is I want you to be very deliberate when you put plus enantiomer, because plus enantiomer is telling you that we have two products that are enantiomeric. So only use this designation when you genuinely have a mixture of enantiomers. Does that make sense? So like if you have like a symmetrical compound, so if you're dealing with something like, so if you're dealing with something like this and you subject it to hydroboration, you're going to get a mixture of alcohols. But are these alcohols enantiomeric? Are these alcohols inherently enantiomeric?
Yes.
Is this center that I've drawn a genuine stereocenter?
No.
No. So it would be more correct to draw the product just like this, because the center isn't even a stereocenter. So it's just important, and this is just one thing I'd want you to note for exams, quizzes, ACS questions. Many of these reactions give mixtures of enantiomers, but it's important that you verify that you're actually getting enantiomers. Does that make sense? Does that point make sense to everyone? Any other questions on hydroboration and the mechanism and regio and stereochemical outcome of hydroboration? Okay, so let's keep going then. And we're going to talk about another very common method to prepare alcohols via acid catalyzed alkene hydration. So let's go over a textbook mechanism for electrophilic addition, where a nucleophilic pi bond is used to form two new sigma bonds. So first, the alkene, in this case, under acid catalyzed conditions, is protonated by forming a carbon-hydrogen bond, breaking our CC double bond. The carbocation is then attacked by the nucleophile, such as water, or any nucleophile really will do the trick. Now, note, the addition of our nucleophile follows Markovnikov selectivity, and the alcohol adds to the carbon that can most readily stabilize a carbocation. So, looking at that two-step mechanism, I'd like us now to draw out a mechanism for the following acid catalyzed hydration of the following alkene. And this will be the last example for this session. So I'd like us to finish strong and apply what we've learned in drawing mechanisms. And let's draw this textbook acid catalyzed hydration. So in the first step, I'm trying to narrate what the student is drawing as accurately as I can. So in the first step, the student drew protonation of our alcohol. Just to be more specific, if you're showing protonation, you should draw the arrow to the carbon hydrogen bond like so. But otherwise, the first step mechanistically looks fine. So you protonate your alkene, and then the student's drawing an oxygen nucleophile attacking. We have a few other student responses submitted in the chat as photos, so I'll take a look at those. Give me one moment to do that. Yep, the mechanism I received looks fine in the chat. Now, the baseline steps for this mechanism look good. Let's try to refine this a little bit and try to reflect the reaction conditions. So we have an oxygen nucleophile. What is our nucleophile in this case for acid catalyzed hydration? What is our nucleophile going to be? Like you drew H3O plus as the acid, that is correct. We just need to adjust the arrows. Our nucleophile is going to be water. So rather than this O minus, let's show water. Let's replace that O minus with water. And you can use like an erase tool, or you can try to redraw it from there. I'll clear out my arrows. So let's try to refine now, and let's show the protonation step and then the attack with our nucleophile. So we're protonating our alkene. And the student very carefully noted that they made a carbocation at the tertiary position. And this is important and very instructive. And if we had to guess and we had to pick a more stable carbocation, which one is preferred, secondary or tertiary? Which carbocation is more stable?
Tertiary.
Tertiary, exactly right. That's why we protonate to generate the tertiary carbocation. Yep. And just to be 100%, that second arrow goes to oxygen. But other than that, it's looking good. We refined now and we noted that water is our nucleophile, and that's what's going to be attacking our carbocation. So let's show the attack. Perfect. We formed our desired carbon-oxygen bond. And there's a methyl on that carbon as well, since it's tertiary. And so now that we have this water installed, let's draw OH2. Okay, and that's cationic. So our next step would be just to pull off this proton. So let's draw one of those oxygen-hydrogen bonds out, and let's pull off our proton to get a neutral species. Just as a general rule, you always want to end on a neutral, non-cationic, non-anionic species. We generally don't isolate cations and anions outside of maybe amine salts or carboxylate salts. So as our final cleanup step, we just deprotonate. And the deprotonation step can be drawn similarly to our first step, where our nucleophile attacks the proton and the oxygen-hydrogen bond breaks to put the electron density back on oxygen. So it looks something like this. So our electron density attacks our electrophilic hydrogen, we pull off our proton, and then the oxygen-hydrogen bond breaks. Perfect. So the student proposed mechanism looks perfectly reasonable. And what I'm going to do now is I'm going to clear the annotations and redraw this just so that we have it saved in the note set, or hopefully it gets saved in the note set when I hit the export button. So our first step, we have our acid, which was very interestingly and appropriately drawn as H3O+, since if you have acid and water, H3O+ generally is going to be the most acidic species. So we protonate our alkene. No stereo control here. We're going to get a mixture of stereoisomers. The next step, water, our nucleophile, then attacks our very electrophilic carbocation. Then from there, to get a neutral species, we're just going to deprotonate our alcohol. And that in turn gives us the following alcohol. And is everyone familiar with what this squiggly line means? So this line typically indicates that at the stereocenter, we have a racemate. So we get a mixture of diastereomers at that center. In this case, it doesn't matter. We just get a single product here. Would anyone like to explain why we get a single product here, looking at this structure? What's special about this structure? It's symmetrical. So as a result, it's not a chiral center. So it would be incorrect to put plus enantiomer here, because by definition, it's not, there's no stereocenter. Does that make sense? So any questions on this example and this mechanism? It's great to see students reviewing these mechanisms from 112 and starting to fine tune drawing out mechanisms in an efficient and effective manner. Any other questions on the topics covered today before we close out this lecture session? So if not, what we'll do is we'll take a quick break and then resume for laboratory.